All right, last video for lesson 9. We want to look at what's called the standard reference cell. And what happens if we change that reference cell. So if we come back to our data booklet, you'll notice this number right here, 0.00. That's the hydrogen half reaction, right? Hydrogen gas and hydrogen ions. That's what we call the standard reference cell, meaning everything is being compared, either it's stronger or weaker than that hydrogen half reaction. It is an absolutely made up and arbitrary point. We could have measured from anywhere. For whatever reason, we chose to measure from that hydrogen half reaction. A good example would be height. So for example, let me show you a little drawing here. So what if you had two people? Person A, person B. Okay. Normally we measure their height from a standard reference point, the ground. So we would measure from the ground up in order to say how tall or short they were. Okay? But that's an arbitrary point. We really could measure anybody's height from any point we want. We could measure from the roof down and say, oh, I'm only negative this many feet and inches, and I'm way more negative than you are. It doesn't change their heights. It doesn't change the difference between them. That all stays the same. It just changes where we're measuring from. Okay, that's the key point. It only changes where we're measuring from. It doesn't change anything about person A or person B. They didn't change. We just measured and described their height differently. Okay? Very similar. We're going to do the same thing with our table right here. We're going to change the 0 point to something else, and then we're going to look at how that affects all of the other numbers on the table. Okay? All right, so let's jump back into, nope, not like that. Back into a whiteboard here. All right, so assume that chromium is the reference cell and not hydrogen. What would be the reduction potential for copper 2 positive plus 2 electrons becoming copper solid for that half reaction in this scenario? So when I do these problems, I always list anything the question mentions, and I always mention hydrogen with it. So, for example, they mention copper. Let me show you this on the table really quick, actually. So they mention copper, so we're going to include that half reaction. I'm going to include hydrogen, because right now it's my 0 point. And I'm going to include chromium, which is right here. Okay? So those 3 half reactions I have to include. If they mention more things, you'd also have to include those. And I want to keep them in that order. So when I write this out, I'm going to put where they are, let's call this the original. Okay? So right now I have copper, I have hydrogen, and then I have chromium. Guess we could be specific here. That chromium is a 2 positive. But it really doesn't matter. You could be talking about the solid or it's just where they're at. The copper in this case originally was at 0.34 positive. Hydrogen is at 0.00. And chromium right now is at negative 0.91 volts. Okay, that's where they are originally. Now the question is saying, well, what happens if we pick a new reference point? What are all those numbers going to be? Now remember in our example, the difference between the heights never changed, even though their measurements do. Okay, so the difference between copper and hydrogen has to be 0.34. The difference between hydrogen and chromium has to be 0.91. Okay? So in our example, they said, what if chromium is the new reference cell? So this is now 0.00 volts. If that's 0.00 volts, and I know that the difference still has to be 0.91, and it's above the 0, I know hydrogen now is at a positive 0.91 volts. Okay, simple enough, hopefully. If I want to figure out what copper is, because that's really what the question is asking, I know copper is another 0.34 above chromium, or above the hydrogen. So again, up another 0.34. So that means that's going to be a positive, where did I write it there? Positive 1.25 volts. Okay, and that's essentially it. Always include everything they gave you in the problem. Always include hydrogen because that's your reference point, whether you're going to go up or down. If you're finding something compared to your new normal, like here, and you go up, you're going to have a positive number. If you were comparing it, and let's say you had, let's add in one more thing. What if we'd also included, let's say calcium. Calcium on my table is at a negative 2.87. Okay? So that means over here, I have to go down more. So I would end up with a negative voltage for whatever that calcium would be. And I don't want to use my brain right now, so I'm going to break out a calculator. So we've got 0.91 negative, 2.87 negative. So that's a 1.96 difference between them, which means over here, it also has to be a 1.96 difference. So this one's going to end up being a negative 1.96 volts. It's like that. So anytime you go above the reference cell, positive. Anytime you're going to go below the reference cell, you're going to be negative. And they could have given me 100 things here. It doesn't matter. That's exactly what I would end up with every single time. Okay? Now, I will give you one helpful tip here, because this tends to show up on some test questions. If they ask me about half reactions, right? All of these half reactions did change, right? The copper half reaction was 0.34, now it's 1.25. The chromium was negative 0.91, now it's 0. Half reaction voltages change if you change the reference cell. But what if I change the net cell potential? Okay, so let's just give you an example. What if I had, using these numbers, what if I had a copper calcium cell? So the copper was the farthest up over there. So I would leave that number, right? So the 1.25 we would leave. It's my strongest OA. So I would have, let me write it over here on the side in a different color so we don't get confused. I would leave it a positive 1.25 volts. Okay. Then I would take the calcium number right here, and because it's my strongest reducing agent, I would flip it. I would write it backwards, I would flip that voltage. So that's going to become a positive 1.96 volts, which would give me 3.21 volts. All right. Now, in order to get that, though, if I used these numbers over here for my new, I would have had to have done all of this in order to find that 3.21 volts. But look what happens if I use the original numbers. Copper's still my SOA. If I leave the positive 0.34 volts, and then I flip the calcium, so now it's a positive 2.87 volts. Let me just double check that I didn't mess this up. I get positive 3.21 volts. So whether you use the original numbers or whether you use the new numbers, if you're looking for the net cell potential or the voltage of a whole thing, a net reaction, not a half reaction, it will never change. So I know there was a question from the homework yesterday about the first, I believe it was the first diploma question from the homework from lesson 8. And it mentioned, what if the standard reference cell was lead? How would that change things? So what they're asking is, what if lead was the 0? Then how would that change the voltage? And the answer is it wouldn't. Right? Changing the reference cell from the old to the new did nothing to the voltage. The overall voltage of any net cell or any complete redox cell, electrochemical cell, will always be the same. So ignore it. Don't do this at all if they're asking you for a net cell potential. If they're asking you for half reaction voltages, reduction potentials, now I've got to do all this to figure out what those new values will be. Okay, hopefully that makes sense. Like I said, if you have any questions, let me know.